Hello, welcome. So, in the previous episode, we added the ability to stall the processor, and this has allowed us to keep the clock running, but single step. And this is very important for implementing this processor in an FPGA, because the FPGA clock is going to run at some large number of megahertz, and we want to still be able to single step the processor in order to see what's happening in it. So I have been able to get this running in an FPGA. I had to make a few changes, but actually surprisingly few. So I think I'd like to do that in this episode, get this all prepared, and yeah. So let's get right to it. There's a bunch of different things that I want to change. One thing to note is that I did slightly alter this circuit. RS latches, apparently you can't do in an FPGA, or at least not the FPGA that I'm using, but it does have a D flip-flop with either an asynchronous set or an asynchronous clear, but not both. If it had both, then it would just be an RS latch. But I've used a asynchronous D flip-flop, and I've tied the set line to 0 so that when it's synthesized, it doesn't use that feature. And I've tied the clear line to reset the D flip-flop. And then I just put a OR gate in here to make it act more like an RS latch. So I think this is probably the way that you would do an RS latch in an FPGA. And in fact, I could probably convert this logic to use this, but I won't do that right now because I could probably use an asynchronous flip-flop with the set feature so that I could set this flip-flop here asynchronously, and that might make the step button work a little bit more reliably at a slow clock, but for now this works just fine. And while this does work just fine for now, there's also other features that might be helpful. One of those is debouncing circuits for push buttons on the FPGA, but currently I've just implemented that in Verilog, but I could implement the debouncing circuit here in digital, and that might be something that I do in the future. So that was some of the changes in the clock control. Another thing that I said was I wanted to reduce the number of signals that come out of the control unit and go to different parts. So what I did was I just overloaded the memop so that it would become 0 when the processor is stalled. I now regret that decision. And the main reason for that is debugging. Now when the processor is stalled, this is always 0 and mem is always 0. So it's not easy to know. Like, I can't just route this out to an LED on the FPGA to see whether or not a memop is actually happening. So I don't really like this decision. So I think I'm going to do it differently. So I'm going to actually implement it the way that I originally wanted to. So now we need an enable signal that is high in order to store, but otherwise everything else is inert in that case. So I think that's good. The other place that I want an enable signal is actually in the register file. So far, what we've been doing with the register file is just simply piping the left-hand side straight through to the result in the case that we don't want to do anything with the result. And that's how we've been keeping the registers from writing a new value. But again, this poses a problem for debugging because now the result is going to be different if we are stalled. And I don't want that. I want to be able to put the result out to some display of some sort and know exactly what the result is. So that means what we really need is on our register file, we need to be able to enable it. And I was avoiding this because I couldn't figure out a clean way to do it until the other day. And actually, it's surprisingly easy. All we need to do is add a selector bit to this decoder, and then there we go. That's how easy it is. So if we are writing, say, 4, oh, interesting. So I upgraded to the latest version of digital, and so it has new features, including floating point, which is interesting. Yeah, very interesting. And they separated these out so it's a little bit easier to see what nibble you're working with, which is an awesome upgrade. Sweet. I like it. So we've got, let's see here. We've got a result, and say it's going to register 0. We don't want it to write to register 0, but currently this is enabled. So our enable signal is backwards, but I think that should be pretty easy to fix. Yeah. But so say we fix that, then when the clock happens, register 0 hasn't changed, which is nice. And that's not, then register 4 or register 0 does change. So we just need to move these down. There we go. Yeah, that works. All right. So now we've got enable signals over here. So the reason I've been using like single letter codes for some of the tunnels is if there's an output by the same name, it causes a problem when it's generating Verilog. So I actually need to rename these 2 tunnels as well. And here, what I want is probably an EN right. Okay, that's working. And now we can revert some of the complication that we put into here. So this one, number of inputs goes back down to 4, and they're all inverted, I think. Yes. We still need this, I think. Yeah, I think so. This I want to move out of this circuit entirely, but I have a few other ideas for that. Okay, so this signal here is no longer required. Okay, that's better. Let's make sure it still works. It appears to. How's our test doing? Oops, not what I wanted. Yes. I see. That's easy enough to fix. That's interesting. Not sure what's going on there, but this one's easy to fix. Oh, I think I know what's going on there too. Okay. And there are 4 bits needed. Okay. Okay. And everything passes. Awesome. All right. Okay. So in the previous episode, I said that we would need to do multiple cycles for memory access. We tried to use block RAM, but that just didn't work. And I actually discovered a much easier way to get it working. And it turns out the solution is really quite simple. So actually, I'm going to convert this into a blockgram, and I'll show you what I mean. So we've got the blockgram, and 2 bits needed. Oh, I didn't set the number of bits. So we've got the blockgram, and the issue was with the load. So we've got a load, and it's working because it's stalled. So if we don't do that, so if we run the processor and we manually clock there. Okay, so here we go. You see that it's loading 0, but there's a 1 there. And the address line is 0. So there's a 1 in 0, but it's not loading the correct value. It's loading a 0 instead of a 1. Well, the solution is actually really quite simple. Oh, you gotta hit run here. So that's the solution right there. We now have a 1 on our data line. Address is still 0. It's the same conditions as before, but we now have the 1 coming out because we're now clocking on the opposite edge. So basically on the falling edge or halfway through the cycle. So as long as we compute the address for data memory by halfway through the cycle, then we can load in the second half of the cycle. And our memory access is essentially one cycle from the perspective of the programmer of this machine. So it does impose some timing constraints on being able to compute the address quickly enough. You have to compute it by halfway through the cycle. But I think that's fine for now anyway. And it allows us to use a blockgram. Now, if we build this in discrete logic, then we can use an asynchronous memory. And so there's a different solution for that. But for in an FPGA, this is all we need to do. And in fact, we could do this to our program memory as well. And that mostly works. And I'll get to that in a moment. But this essentially solves the problem. We don't need to do a multi-cycle load or store. We can just invert the clock and boom, we've got blockgram working. So I think that's what I'm going to do. Another thing to change is the blockgram in the FPGA. It isn't quite this big. It only has 14 address bits. Specifically, I'm using an up5K, ICE40 up5K. So that has actually what's called SPRAM, single ported RAM. It works essentially the same as this, but it has a single port and it only has 14 address bits. There's more than one, so we could chain more than one into a larger memory, but for now, 14 address bits is totally sufficient. So I'm just going to change this to truncate the address. There we go. Oh, and I also have to change this to 14. And that's still working. Awesome. So we have our data RAM now being mapped to block RAM. And this will actually run and synthesize in an FPGA because the EEPROM gets turned into a series of LUTs. And for a small program, that's probably just fine. In fact, it might even be better because it will look at the program that's in the EEPROM and it'll simplify the processor. It will remove any logic that's not necessary to run that specific program, which is kind of neat. But I'd like to see if we can get the program memory to also be block RAM. And it's actually fairly straightforward. I already figured out how to do it. Oh, I know what's wrong. There we go. So this appears to be working. And even our tests seem to pass. I say seem to because there's actually a subtle problem with this. So we have our program in block RAM, and this is proper block RAM, not the SP RAM over here. And this can be initialized with a program on the FPGA. So that's all good. And our test suite is passing, so that's fine, right? Well, sort of. And it might be easier to demonstrate if I do this. So one thing you'll notice is the display is blank when the processor first comes on. That's interesting. What's going on there? And now we've clocked, and we've got our move instruction. Okay. Let's clock down to our jump and see what's going on there. Okay, so here's our jump. Oh, interesting. The display cleared out again. That's very interesting. What could be going on there? And then our program counter is 3 now. Okay. And here's our add that we're expecting to happen after the jump. But why did the display clear out? That's interesting. So let's actually change our program slightly. Let's put something after the jump. Let's put something really obvious. Let's actually just break our program. Okay, and we make, all right. Now, let's go back to that jump and see what happens. Okay, so here's our jump. We're going to jump to 3, and oh, look at this. We have a move here as the next instruction, and it's moving 0 into R1. And now here's the add that's coming next. So that's what the problem is. And unfortunately, none of the test cases seem to catch this issue. So what's happening is what's called a branch delay slot. So we've inadvertently pipelined the processor. And this is the branch delay slot. It's also sometimes called a branch shadow. What ends up happening is the processor is moving through, it loads this instruction, and because the block RAM has a register in it, it's already started loading this instruction. So when it figures out, oh, I need to jump to .loop, I need to jump up here, what it does is it changes the program counter to that up here, but the memory's already loaded this move instruction. So then it does the jump, and the jump does happen, but the very next instruction gets loaded and executed. And that's where the problem is. So I don't really want that to happen. There's a number of different reasons to not have that happen. So it would be good to get rid of this. Well, probably the best thing to do is actually detect it. So what I'm going to do is I'm going to halt the processor right here, 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 and here. That way, if there's a branch shadow, we've got 3 chances to detect it in our tests, and this should error our tests. So let's regenerate that. Oh, by the way, I did add a run line to the test programs so that they will handle the stall situation properly. So let's switch to our test suite. And we've got our program with the halts in there. And now jump fails because it hits a halt and errors out. So that's what we want to happen. Okay, so how do we fix it? Well, if we're jumping, what we want to do is we want to do basically a no-op. So one of the things that we could do is just make 0 into our no-op. And so if we start the processor, we see that we've got a no-op here, or a NOP. So then how do we make sure that when we branch, we can insert a NOP? Well, it's actually quite easy to do. And here we just insert our 0. And, well, we want to do that when we jump. So let's do that. What's going on here? Oh. Mm-hmm. There we go. There's a wire a little bit longer right here that was causing that problem. Okay, so we have a knot being generated here. Let's see if our branch shadow is better. Oh, we have to actually run the processor to do this. Logic seems to oscillate. Interesting. Interesting. So now what's happening is when the jump instruction happens, the jump line goes high. When the jump line goes high, we insert a knot. When we insert a knot, the jump line goes low, which stops inserting the knot, and then we've got to jump again. So we need to fix that. And probably the easiest way to do that is just to add a register. Let's do that again. Okay, now let's see what happens. Here's our jump, and we can see the instruction register is still producing the jump instruction at 61, and then the incoming one should be our move instruction, but we should get a 0 instead, which is exactly what happens. We now get a knot. Actually, that knot is... let's just see that again. So there's our jump, line's low. When this goes high, we should see our knot, which we do, and when it goes low, knot should be done, but we get 2 knots. Interesting. That's what I thought was happening. Is there some weirdness going on here? That's what I'm wondering. Okay, here's our jump. We have our jump is 61, and we're storing a 0. Good. And we have 313 coming in. So we should skip the 313. All right, now we have 0 still. Our RAM is giving a 0. Oh, I think I know what's happening. We're actually doing a double pipeline because this is pipelining it and this is pipelining it. So we're actually doing it twice. So I think the solution will probably be just to do this again. So what was happening was the jump instruction was being fetched from memory and then going into the instruction register in the next cycle. So the address would select the jump instruction's location, and then the jump would be executed and it would load the move that we put in there to cause a bug. And then that would be negated, and then the program counter would load the next one too before the jump happened. So there was a 2 branch delay slots instead of just 1. So I think by inverting the clock, we should have fixed that. Let's see. So here's our jump. Our jump is at C, which C is the location of the move. So C is the 313 and B is actually the jump. So let's see if this moves to D, because if it moves to D, that is incorrect. It does not. So here's our knot, and we should be loading the next one. Yeah, it's being applied. 8092, I believe, is correct. That should be at 3. Yes, that is correct. And here's our add. Awesome. Okay. So we've successfully pipelined the fetch. And I said I wouldn't pipeline this processor, but I feel like pipelining the fetch, if it's only this much logic, it's really not that bad. We might have a bit more logic to handle the program counter properly, because the program counter is now pointing past the current instruction. It's pointing at the next instruction. But that is relatively easy to fix. So let's also check and make sure that our tests pass. Jump failed. Interesting. That's not what I was expecting. Now they pass. Okay, that's better. Okay, let's actually move this logic into the fetch. And it still passes. Awesome. Okay, so we now have a processor that is synthesizable into an FPGA. There is one issue though. If I export this to Verilog, let's just put it in here. No Verilog code for button available. And in fact, these displays don't have any Verilog code either. And we're using a divide in here somewhere, not in this one, in this one. And these divisions are not going to work on an FPGA, at least not efficiently anyway. I don't think that there's a way to synthesize a single cycle divide. I could be wrong about that, but this will drastically slow down the clock rate if it does synthesize. And I'm skeptical about that. Actually, I suppose we could try it. Save, export to Verilog. Let's try it. No Verilog code for div available. Yeah, it doesn't even try. So, given that, what we really need to do is extract out the processor itself into a separate embedded circuit. So that ended up taking a lot longer than I thought it would. So pardon me if I just edit it out. There's no new functionality. I just moved things around and renamed a few things. So I don't know how much you really want to watch that. Just in case you do want to watch it, I will put the footage in an unlisted YouTube video that I will link in the description below this video. So if you really do want to watch me refactor this and pull out the CPU, then you can do so. For those of you who don't want to see that, I will just show you around. So this is now starting to look a little bit more like a CPU. So what I did was I extracted the CPU proper into this file, and I set it up to be a layout shape. And the way layouts work in digital is the direction of the labels on the pins indicate which side it's going to appear on. And the order goes from left to right or top to bottom. So if you want to change the order, you just take something and you drag it. So that's the way that layout works. And what I've done is I've just pulled any relevant signals that I want to pull out to a pin. I just named them, and I decided on a standard naming convention of just putting _T on here. For whatever reason, digital doesn't allow you to have a tunnel and a pin with the same name. It'll complain. And I think because internally it's not merging the nets, so it doesn't realize that the output and the tunnel are the same. So in the Verilog, to avoid a naming conflict, it just tells you can't do that, even though technically it probably could. But anyway, because of that, anything that's going out to an output pin, I just put _T on it. And I pulled out all of the signals that we want to use for our blinking lights. And I also included the clock control circuit in here, but I pulled the memory out. And there's a reason for that. What I want is a little bit more control over how the memory is handled in Verilog. So with no memory in here at all, then I can wire up the memory in a separate Verilog file, and that just makes things easier. So this does export to Verilog. I have tested it out. See, if there was a problem, it would have errored, and it does not. So that's a good thing. So this should now run on an FPGA, no problem. And in here, we've got our memory. And the nice thing about having the memory broken out like this is if we're running the program, then we can see in here what the contents of the memory is. And of course, we can see our usual blinking lights. Now, this does mean that we'll probably want to pull out a lot more signals and route them to LEDs so that we can see what's happening inside the processor, because unfortunately, you can't look inside of this chip while it's running. You have to actually stop it, and then you can look inside. And you can run this, but this doesn't have any memory hooked up. So yeah, there are not ideal things about this situation, but I think this will work for now, and we can always revert it if we really don't like this. So I think that is everything. Again, if you want to see me actually pulling the CPU itself out into an embedded circuit, you can watch that video in the description. Thank you very much for watching. I hope you have a great day. Bye.